Until now, we've only seen examples of supervised machine learning. Today, we'll get an introduction to unsupervised machine learning. Specifically, we're going to learn about clustering by using the clustering.jl package. Even more specifically, we're going to learn how to use the k-means clustering algorithm. So, what's the difference between supervised machine learning and unsupervised machine learning? And what's the deal with another subject starting with the letter K? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
At the very beginning of this series, we learned that the major subfields of machine learning are supervised learning, unsupervised learning, and reinforcement learning. By now, you should have a pretty good idea what supervised learning is, and you should be comfortable using several different supervised learning algorithms. According to the Wikipedia article on unsupervised learning is a type of algorithm that learns patterns from untagged data. Whether you realize it or not, all of the datasets that we've used so far in this tutorial series have been labeled data. In other words, there's some input or feature data that results in some output or labels. And the goal of supervised learning is to use that labeled data in order to create a model with parameters that can make predictions. But a lot of data, if not most of the data in the world, is unlabeled data. So while supervised learning may be very impressive, it's no good unless someone goes through the trouble of labeling all of that data, which may not be practical for large datasets. This is where unsupervised learning comes in. The motivation behind unsupervised learning is to answer the question, if you present unlabeled data to your computer, can your computer find something interesting in that data? Unsupervised learning is not about making predictions. Rather, the goal of unsupervised learning is to extract knowledge from an otherwise chaotic world. There are many different subfields within unsupervised learning, but the two major ones are clustering and dimensionality reduction. We'll cover dimensionality reduction in the next tutorial, but in this tutorial, we'll learn about clustering. According to the Wikipedia article on cluster analysis, clustering is the task of grouping a set of objects in such a way that objects in the same group, called a cluster, are more similar to each other than to those in other clusters. It is a main task of exploratory data analysis, and a common technique for statistical data analysis used in many fields, including pattern recognition, image analysis, information retrieval, bioinformatics, data compression, computer graphics, and machine learning. Cluster analysis itself is not one specific algorithm, but the general task to be solved. Clustering can trace its roots back to the 1930s, when it was originally used in anthropology and psychology. In machine learning, clustering falls under unsupervised learning. There are many different clustering algorithms, but perhaps the best known and most widely used is the k-means clustering algorithm. The idea behind k-means clustering is to take your entire dataset and partition it into k clusters, k being an integer greater than or equal to 1, but less than or equal to the number of samples. The term mean refers to the average of all of the samples within a cluster. The objective of the k-means algorithm is to assign all of the samples in a dataset to one of the k clusters in order to minimize the within cluster sum of squares. here's what the actual objective, or cost function, looks like. Because it uses distance calculations, the k-means clustering algorithm has some similarities to the k-nearest neighbors algorithm. But the k in KNN refers to the number of samples nearest to a data point, while the k in k-means clustering refers to the number of clusters that partition all of the samples in the dataset. Like other machine learning algorithms that we've seen in the past, the k-means clustering algorithm is an iterative process that seeks to minimize a cost function. The difference with the k-means clustering algorithm is that there are only inputs and no outputs. This is true for all unsupervised learning algorithms. Let's walk through an example to better illustrate the concepts. For this tutorial, knowledge of Julia and VS Code is required. I'm also assuming that you're watching this entire machine learning playlist. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called ul_kmeans.jl. Launch the Julia REPL by using Alt-J, then Alt-O. For this tutorial, I'm going to dock the REPL panel in the same panel as my editor. In the REPL, change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the following packages: clustering, plots, and R datasets. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. Okay, let's get started. Let's start by loading some packages. Now, let's generate a plot using some random numbers. Using a random seed is optional. I'm using it so I can reproduce my results. You should see a plot with 100 random points. This plot represents a two-feature dataset. If you had to partition this data into two groups, how would you do it? Unfortunately, there's no easy way to do it visually. This is where k-means clustering comes in. In order to use the k-means clustering algorithm, you need to provide your input data horizontally rather than vertically, meaning that each row is a feature and each column is a sample. This is similar to how we loaded data into other machine learning models. I'm not sure when this happened, but it looks like the transpose function is part of Julia Base now. In prior versions of Julia, the linear algebra standard library was required, but it clearly works without it. I guess I need to pay a little more attention to the update notes when Julia releases new versions. In any event, let's move on. This is the k in k-means clustering. Using a value of 2 indicates that we want to create two clusters. The k-means clustering algorithm is an iterative algorithm, so we do not need to write our own for loop. The algorithm will stop when it converges on a solution. But depending on your dataset, it may take a lot of iterations. So to prevent an infinite loop, you can set a maximum number of iterations. Using a value of 100 tells the algorithm to stop after 100 iterations. I'm resetting the random seed since I've already generated some random numbers, and the k-means algorithm also uses random numbers. The k-means function is the main function for the k-means clustering algorithm. Most of those arguments are self-explanatory. That last argument displays the iterations in the REPL. Let's take a look. So it looks like it only needed 4 iterations to converge on a solution. That second column with the objv header shows the value of the cost function that the algorithm is trying to minimize. The third column shows the delta between the iterations. You can see that the algorithm stopped when the change was 0. The clustering package provides some useful information about the results. The algorithm assigns an integer between 1 and k for each sample, indicating which cluster it's been assigned to. It's a little difficult to see in the REPL, but don't worry, we're going to plot these values in a minute. These are the counts for each cluster. A naive approach would have been to create 2 clusters with 50 samples each. But as you can see, the algorithm found a better split that happens to be a 40-60 split. These are the x and y coordinates for the 2 centroids for the 2 clusters. The lowercase Greek letter mu is used to identify the centroid of the cluster. It's a little difficult to tell which are the x and y coordinates since this happens to be a 2x2 matrix. But the first row contains the x coordinates, and the second row contains the y coordinates. So the first cluster has a centroid at approximately 0.7, 0.2, and the second cluster has a centroid at approximately 0.4, 0.7. I realize that this is all very abstract, so let's plot these clusters. This is the exact same data. All I did was make the marker size larger so they're easier to see. Also, I added different colors so you can see the different clusters. Cluster 1 is blue, and cluster 2 is orange. Let's see where the centroids are located. You should see 2 yellow circles, which indicate the location of the centroids. Pretty cool, right? Let's repeat this process using different values for k. Go back up to line 42, or whatever line it is in your editor, and change the value of k from 2 to 3, and then rerun the code until you get an updated plot. You should now see 3 clusters with 3 centroids. If you go in the REPL, you'll see that it took 5 iterations to converge on a solution. You'll also see all of the relevant information about these clusters. Let's repeat this process for k equals 4 and k equals 5. You should now see 4 clusters with 4 centroids. You should now see 5 clusters with 5 centroids. I'm going to delete the plots without the centroids, and then flip between the different plots. Pretty amazing, right? So the k-means clustering algorithm is able to identify clusters even in random data. Now that you know the basics of using the k-means clustering algorithm, let's save our plots and then move on to seeing an application of the k-means clustering algorithm. For this section, we're going to use a dataset from the R-Datasets package. Let's take a look at this dataset. This dataset contains 97 samples of weight taken from male cats. The column named BWT contains the body weight in kilograms, and the column named HWT contains the heart weight in grams. This is an example of an unlabeled dataset. Even though there's a column containing the gender of the cat, they are all male, so it doesn't provide any additional information. Let's plot this data to see what it looks like. As you might expect, it looks like there's a linear relationship between the body weight and the heart weight. But rather than performing linear regression on this dataset, let's partition this data into 3 clusters. For example, maybe you need to group these samples between small, medium, and large breeds. If you had to select 3 groups manually, how would you do it? First of all, notice that the unit of measures is different between the 2 features. They are both weight measurements, but the body weights are in kilograms, while the heart weights are in grams. So the values of the heart weights are larger, even though they weigh less. Let's apply our knowledge of feature scaling to scale these values between 0 and 1. Now that we've normalized our data, let's replot it. I'm just going to copy and paste the plotting code from above and make a few changes. As you can see, it's the same data, but the values along the x and y axes all between 0 and 1. Okay, we are now ready to apply the k-means clustering algorithm to this dataset. Let's start by initializing some variables. This time, let's start with a k value of 3 since we want 3 clusters. But let's set the ITR value to 1 just to see what it looks like after one iteration. We need to set the random seed again since we've used the random function already. This is the exact same code that we used earlier with our random datasets. Now that we have our results, let's plot it to see what it looks like. So that's interesting. Let's take a look at the centroid locations. So that's interesting as well. Bear in mind, this is how the results look after only one iteration. This isn't necessarily how the clusters and centroids will look after the model has converged on an optimal solution. Go back up to line 136, or whatever line it is in your editor, and change the value of the ITR variable from 1 to 2, and then rerun all of that code. I'm going to delete the plot without the centroid, and then flip back and forth between the two plots so you can see the differences. So there were a few changes to the cluster assignments, but there were some major changes to the centroid locations. What you're seeing is a visualization of the iteration process. The k-means clustering algorithm seeds the initial location of the three cluster centers, and then calculates the Euclidean distances between it and the samples within the respective cluster. With each iteration, the algorithm moves the location of the cluster center in order to lower the value of the cost function, which may result in different samples being assigned to each cluster. The algorithm will continue these iterations until it converges on a solution or until you tell it to stop. I'm going to repeat this process a couple more times so we can plot a few more iterations. I'm going to fast forward through this part. I'm going to delete the plots without the centroids, and then flip through the 4 separate iterations. That's pretty interesting, right? You're seeing the convergence process in action. If you go into the REPL, you'll see all of the relevant information. As you can see, it's not an even split of the samples. 38 samples were assigned to cluster 1, 38 samples were assigned to cluster 2, and 21 samples were assigned to cluster 3. If you look at the plot, cluster 1 is blue, cluster 2 is orange, and cluster 3 is green. I went through that pretty quickly, so let's save our plot and then go through a recap of what we just saw. As a way to summarize what we just saw, let's do a side-by-side comparison between the k-nearest neighbors algorithm and the k-means clustering algorithm. The names are very similar, so you can be forgiven for confusing the two, but the algorithms are used for very different purposes. KNN is an example of supervised learning, while k-means is an example of unsupervised learning. KNN is used for classification, while k-means is used for clustering. KNN uses label data, while k-means uses unlabeled data. The k in KNN refers to the number of samples nearest to a data point, while the k in k-means refers to the number of clusters used to partition all of the samples. KNN may be used to make predictions, while k-means does not make any predictions. Although the examples that we saw today use two-dimensional feature sets, you can use k-means with any number of features. On the surface, k-means clustering may appear to be too simple to be useful, but it is in fact a very practical tool. Many business applications do not require precise models that are 99.9% accurate. You often encounter large datasets that don't have any labels, and you just need a way to simplify it so you can better understand what you're looking at. In any event, I hope you enjoyed today's introduction to unsupervised learning. I'm afraid that I don't know the original author of the clustering.jl package, but it's a fairly large package that supports a lot of different clustering algorithms, in addition to the k-means clustering algorithm. Please be sure to show your appreciation to the developers and the contributors by going to the GitHub page of clustering.jl and leaving them a star. Well, that's all for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.